Okay, more series. 10.8 is about, it's called Taylor and Maclaurin series. I'm just going to call it Taylor series because Maclaurin, after all, is just a special case of that. Now, what's the difference between this and what we talked about in the last section? In the last section, we talked about a Taylor polynomial of degree n, and this is called a Taylor series. And that means Taylor infinite series. So, here's the definition. The Taylor series for f of x at x equals x sub 0 is given by, let's see, what do we have? We have the function itself at x sub 0. This is the same recipe from last section, plus the derivative at that point times x minus x sub 0, plus the second derivative at times x minus x sub 0 squared over 2 factorial, plus, and then dot dot dot, and instead of going up to the nth, it's dot 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 forever. And a little bit neater way of writing this would be to say that it's the sum from k equals 0, notice that I'm starting at 0 here, to infinity, of what does one of these look like? One of these looks like it's the kth derivative at x sub 0 times x minus x sub 0 to the k over k factorial. Right? In sigma notation, instead of writing all these out, we could just write it in summation notation and let it go to infinity. So you could check, make sure that this works. If we plug in 0, 0 factorial is equal to 1, and then this would be the 0th derivative. Well, the 0th derivative is the function itself, right? No derivatives at all, so that would be f of x sub 0, and then something to the 0 power is 1, so yes, we in fact do get this term, and then so on and so on. You can check the other ones, but it should be pretty clear that we're taking the kth derivative, kth power, kth factorial, right? It's a pretty easy recipe. And that means the Maclaurin series looks the same. For the same function, it would just be the sum from k equals 0 to infinity of the kth derivative at 0. All I'm doing is plugging in 0 everywhere we see an x sub 0 and x to the k over k factorial. Right? Same idea, just the x sub 0 is 0. Okay, well, what does this mean? What does it mean to have a polynomial of infinite degree? Well, the question is this. It all comes down to, do these things converge or not? This is why we learned so much about convergence in the first half of this chapter. So we can determine if we can find the series for some function, then can we figure out where it converges? So let me give you an example. Here's a function. F of x is equal to 1 over 1 plus x, which is, incidentally, for taking derivatives, that's x plus 1 to the negative 1. Now this is one that we're going to be familiar with. We'll talk more about that later, like recognizing these series later on. But let's say we didn't recognize anything and we actually had to take the derivatives. Now hopefully for writing, we're going to do it at x equals 0. We would like to be able to write this. Okay, so let's see if we can take a few derivatives and recognize some kind of pattern. So there's the function, and when you plug 0 in, that's equal to 1, right? And what would the derivative of this be? It would be negative 1 times x plus 1 to the negative 2 and then the second derivative is, let's see, that'd be negative 2, so that'd be negative 2 times negative 1. The negatives cancel out over x plus 2 cubed. And this is going to be negative 3 times 2 x plus 2 to the fourth derivative be equal to positive 4 times 3 times 2. You can try taking these derivatives yourself if you want to do more work, but this is what's happening. And then, see what's happening here? It looks like the nth derivative. If we wanted to dot 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 this, the nth derivative would be equal to, it's like n factorial over x plus 2 to the n plus 1, and then they're alternating, so let's see, times negative 1 to the n. Now this was the first derivative and it was negative, so the n, that looks like it's right. I don't have to put a plus 1 there. Alright, let's try writing the first few terms of this out and see if we can recognize what's going on here. So the series is going to look like this. It's going to start with whatever the value of the function is, which is 1. Right? And then we have the derivative of the function. What do you get when you plug? Why do I have all these x plus? What's going on here? Why are those 2's? Jeez. You're wondering to yourself, what the heck are those doing there? Good for you, because they should all be x plus 1. I don't know where those came from. Sorry about that. Take a second to go back and fix that. When I plug 0 into this, I get negative 1. Right? Times x to the 1 over 1 factorial. When I plug 0 in here, I get 2 times, this is the second term, right? So that'd be x squared over 2 factorial. And then here, when I plug 0 in, I get negative 3 times 2, or 3 factorial, times x cubed over 3 factorial, plus, when I plug 0 in here, I get 4 factorial over, times x to the 4th over 4 factorial, etc. So it looks like every single time, because of the way the derivatives of this worked out, these are canceling out. So my series is 1 minus x plus x squared minus x cubed plus x to the 4th, and so on. Now, can you come up with what this would look like? I'll start it off here. K equals 0 to infinity. And I'll give you a second to try to figure out what it would look like. Okay, it's going to be x to the k, and then it's alternating, so I need a negative 1 to the k, and then try plugging 0 in. Remember, we're starting at 0. When I plug 0 in here, I would get a positive first term, or 0th term if you want, and that's correct. So that's what it looks like. That's how we would write it in sigma notation. Okay, now here's the question. Does this converge? Or, better to say, where does this converge? And you're wondering what sense of the word where I mean? Like in America? In Canada? On a European continent? No, when we say where, we mean for what x values. Okay, so we're going to do the ratio test. To answer this question, we are always going to do the ratio test. What does that look like here? Well, we're interested in finding the limit as k approaches infinity of the k plus 1 term over the k term. So take a look here. That the k plus 1 term would be x to the k plus 1, and for the alternating things, we just throw the alternating piece away. We'll consider that later. And x to the k. So this is a fairly simple one. The ratio test just comes down to this. We always disregard the alternating piece. And then simplifying that, the limit as k approaches infinity of x to the k plus 1 over x to the k is just x. Okay, now where do we go from here? We used to get like a number here for this limit, and now there's an x in here. And notice that this, the k approaching infinity, there's nothing in here, right? There's no k's in here, and x is not part of this. So the x can actually come to the outside because it's not part of this, what's happening with the k's. When I bring that to the outside, when I factor that out, it's like there's a 1 left behind. Well, this is a kind of an odd question, but what's the limit as k approaches infinity of 1? Well, it's just 1, right? So x times 1, that's just x. So this all just turned out to be an x. Now, when we did the ratio test, what did we want this to be for convergence? We needed it to be less than 1. And here, especially because of the possibility for alternating series, we need the absolute value of this to be less than 1. Or in other words, whatever we get here needs to be in between -1 and 1. So what does this mean? This series converges from -1 to 1. For x values between -1 and 1, this series will converge. For other x values outside, it's not going to converge. What that means is, remember the graphs we looked at in 10.7? It means those graphs, we can get it to hug tighter and tighter to the function between -1 and 1, right? As we go dot, dot, dot to infinity. In fact, when we dot, dot, dot it to infinity, this series really is equal to the function, right? But if you go outside between -1 and 1, then no good. Now there's one extra little thing that we have to do because of the different types of convergence that we've seen and the fact that we threw the -1 out, especially here. We need to check the endpoints. We need to check, because maybe it would converge actually at one of these. Check -1 and 1. Now what does that mean to check them? It means we actually are just going to plug them in and see what the series looks like. So when x equals, I'll check the 1 first. When x equals 1, what does this series look like? It looks like you plug 1 to any power, it's just going to be 1, and then it's just going to be alternating. It's going to be 1 minus 1 plus 1 minus 1. Right? This is just going to do its sign flip-flopping. Does this converge? No. Remember, the terms have to go to 0 for it to converge, so that diverges. And then for x equals -1, when x is -1, let's see, that would be like -1 to the 0 power is 1, right? Well, it'd be like -1 to the k times -1 to the k, which is like negative 1. So you're always going to get the same sign for these two things. So it's actually going to be 1 plus 1 plus 1. It's going to diverge in an even more divergent fashion. So what does that mean? It means we do not put equal signs under either of those. It means this converges from here to here, and it does not include those endpoints. If we found that it converged at either of those, we'd just throw an equal sign under one of those. Okay? Sorry, I'm out of room on this page. Let me just do this. So a little bit of vocabulary here. So for this problem, we say that the interval of convergence is negative 1 to 1, or you could write it like this, right, in your fancy calculus interval notation. We say the radius of convergence is, what do you think it is? Well, the center of this interval is 0, right? And it's like 1 on either side of that, so the radius is 1. All right? And notice that the center of the interval, hence this was a Maclaurin series at x equals 0. Wherever you're finding the series, that's going to be the center of your interval, right? No exceptions. Okay, let's do a couple more examples. Your head might be spinning a little bit right now. I'm going to take a couple examples from the book. If we're given this, so given k equals 0 to infinity of the series x to the k over k factorial, we want to find the interval and radius of convergence. Well, right off the bat, we know the center is going to be at 0, right? Because that's just an x. It's not like an x minus 1 or something. If it was x minus 1, then the center would be 1. All right, so by the way, the College Board loves questions exactly like this, as you will see when you do your practice multiple choice. So, ratio test. We want to find the limit as k approaches infinity of the k plus 1 term, which would be x to the k plus 1 over k plus 1 factorial, divided by that term, which is the same as multiplying by the reciprocal. Don't get lazy and leave these little limit things off, because that could cause you problems. X to the k plus 1 over x to the k is x. K factorial, k plus 1 factorial, that leaves a k plus 1 on the bottom. Now, just as in the last example, k is going to infinity, not x. So x, let's bring that out here. So let's see, that's 1 over k plus 1 left on the inside. And what's the limit as k approaches infinity of 1 over k plus 1? Well, as that goes to infinity, highest power is on the bottom, that's going to go to 0. And that's just 0. So here's a question. I mean, what values of x? So we want x times 0 to be in between negative 1 and 1. What values of x does this work for? This works for all x values, right? It doesn't matter what x is. 0 is always going to be in between those. So what's the interval of convergence? This converges everywhere. That's our favorite kind of Taylor series. it converges everywhere. So as you go dot, 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 whatever function this happens to be equal to, this series converges to it everywhere. It won't just hug it for some little interval, it will hug it forever. It will actually become the function on its entire domain. Now, that's cool. Let's try another example. How about k equals 0 to infinity of k factorial times x to the k. So we're taking the factorial and putting it up there. You might think for a minute what effect you think that might have on convergence. So we want to do the same thing. We're going to find the interval and radius of convergence. So we go to the ratio test. We're trying to find the limit as k approaches infinity of the k plus 1 term over the k term. That equal to k plus 1 times x, right? There's one x on the top and there's an extra k plus 1. And I'm going to bring the x to the outside because it doesn't have any business inside this limit, which only involves k. And as k approaches infinity, k plus 1 approaches infinity. So that's x times infinity. So we need this. Well, that's going to be kind of hard to do. In fact, the only number that will work for this is if you make x equal to 0. Then that'll knock that out, right? But that's it. So this series converges at x equals 0 only. So we went from seeing the best to the worst. Here's one that converges everywhere, and here's one that only converges at the center of the interval, only at that one point. So let's do one more example and see what it looks like when we have the in-between. Let's see, how about this? K equals 0 to infinity of negative 1 to the k, x to the k, over 3 to the k times k plus 1. Well, that's kind of crazy looking. Let's see if we can figure it out. Where does this series converge? All right, we have the k plus 1 term, and remember the alternator, we throw that out when we're doing the ratio test. We'll come back when we have to check the endpoints. If we do, then that will be important then, but not now. So we leave the sign flipper out. So that's x to the k plus 1 over 3 to the k plus 1 times, when I put k plus 1 in here, I get k plus 2, right? Divided by, or multiplied by the reciprocal, 3 to the k times k plus 1 over x to the k. Okay, doing some canceling here, and you know I'm going to bring my x to the outside, so we just could go ahead and do that now. Right, there's one x there, that comes to the outside. The k, this many 3's and this many 3's, I've got one extra one on the bottom. And then I've got k plus 1 here and k plus 2 here. So, what's the limit as k approaches infinity of k plus 1 over 3 times k plus 1? Same power, top and bottom. There's a 3 on the bottom. So we do the coefficients, it's 1/3. So that's x times 1/3. Now I need this. to be in between -1 and 1. And of course I want to know about x, not x over 3, so multiplying through by 3, that gives me -3 to 3. So that's interesting. This has an interval of convergence from -3 to 3. But we have to check the endpoints. So check 3 first. And now this is in play, okay? If x is equal to 3, then I have the sum of, let me write it out. I won't take any shortcuts here. With a little bit of practice, you might forego this step. I would have -1 to the k over 3 to the k, sorry, times 3 to the k over 3 to the k times k plus 1. Those cancel out, right? When I say check 3, I'm plugging 3 in for x. And then I would just have a series that alternates. It's an alternating over k plus 1. So let's write out a few terms and see if we recognize that. When I plug in 0, I get 1. When I plug in 1, I get -1/2. And I get the alternating harmonic series. Does that converge? Yes, it does. It converges conditionally, right? But it's alternating and the terms are going to 0. So this converges. So what does that mean here? That means that it converges at 3. Right? We check that endpoint, so we have to put an equal sign there. It does converge at the 3. Now let's check -3. And likewise, can you see what? Yeah, I can see that. K equals 0 to infinity. -1 to the k times -3 to the k over 3 to the k times k plus 1. Well, since these are both to the same power, the k power, it's like these two negative signs cancel out. Or if you like, you could say like 3 to the k cancels out with 3 to the k, leaving just -1 to the k. And -1 to the k times -1 to the k, since those are always the same sign, both positive or negative, what we're going to get is the harmonic series, right? Because we plugged in -3, it didn't alternate this time. And you know that, even though it does so slowly, that diverges. So, no equal sign there. Bam, there you go. The interval of convergence for this is from -3 to 3. And notice the center, it is centered at 0. All right.